Let us move to next lecture. This is what we were planning to do. That was the 2D representation of three-dimensional molecules, how to represent them. Okay, so first is perspective. Perspective is perfect. Whatever you see, you draw. You write everything. Whatever you see, you draw. Bonds which are directed away from you behind the plane of paper, you put it as dash. Okay, whatever coming towards you, you put it at wedge. And you can have as many wedge, as many dash, doesn't matter. Right? So it was a very clear perspective vision. But as it is very clear, it will never be used in exams. They want to be a little more complex for us. Wedge dash. In wedge dash, they consider that the chiral carbon and the two bonds, these, are to be maintained in the plane of paper. The bonds which are in the plane of paper are represented by simple line, like this. And the bond coming outside are represented by a wedge. Going behind are represented by a dash. Okay. So, simple line in the plane of paper, dash behind, wedge is P forward. This is with one chiral carbon. With more than one chiral carbon, you can have similar idea with respective one carbon, two bonds in the plane of paper, other two are in and out of the plane of paper. Absolutely clear? Okay. Then we move to fissure, which is the most important for us. Now here, only the central carbon is kept in the paper plane. No other bond or atom are assumed to be in the paper plane. Only the central carbon, this. Okay. The two groups which are directed away from us are placed on vertical line, O and W. Those which are on horizontal line will be directed towards us. Cross section of horizontal and vertical is in the paper plane, the chiral carbon. And in the molecules, if there are more than one chiral carbon, then the longest carbon chain is placed in a vertical line. Now, this is again for particularly two chiral carbon. I can exemplify. Fissure always is the eclipsed conformation. That is a rule. The carbon atom with highest oxidation state is to be placed on the vertical top or closest to the vertical top. Right? This I can exemplify from aldehyde or aldose and ketose sugars. Like if you see aldose sugars, CHO is kept on the top. And for ketose sugars, the C double bond O is kept second to the top. Right? So either to the top or closest to the top is what we can say. Now when I say fissure always represent eclipsed conformation, why I want to emphatically make a point here. See this. Okay, it is entirely your choice where you want to keep the structure. My suggestion is simplest is these vertical placed down, eclipsed conformation. So if I see this, you have to mark this is the front one and this is the back one. So this is the back one and this is the front one. So if I take this front, then P is left hand side, R, R, G. Why I'm saying this? When they give you some random arrangement like this, okay, you cannot convert it directly to the fissure. First, you rotate it to eclipse. And then only you can have the structure drawn. Okay. Though my best suggestion is don't go for that thing that how to visualize, which to put on vertical line, which to put on horizontal line. My suggestion is just do the RS nomenclature. You get this bond is R or S. And then in the fissure, you check, okay, this is the one I'm considering back. So configuration should remain same. This is the one I'm considering front. Configuration should remain same. That is the safest way, time-saving method, because we are in an objective exam. In objective exam, fissures are already drawn there. You don't have to draw. You have to just check. So please follow the idea of RS configuration. I will tell you how to check the RS configuration, that I'm going to tell, but that is an easier and a faster way to interconvert such Sohars wedge dash arrangements. Okay. And bring them to Fisher. Right? First, the rules that we were using. See, CHO closest to the vertical top, CH2H bottom. These are all horizontal lines. Longest carbon chain on the vertical line. So when I say this way, so I'm rotating this structure in the plane of paper upside down. This is going down, this is going up. Okay, so 1, 2, IUPAC numbering, 3, 4, 5, 6. Here it becomes 1, 2, 3, 4, 5, 6. In 2, this was right, so here it has become left. Right? So conventionally, this structure is incorrect and this structure is correct. But when you have to give 4 options, conventionally correct can only be 1 option. So definitely you have to know how to identify, okay, these are molecules are same. Right? That skill we need to develop, because with conventionally correct concept, they will have only one as a structure, which is not possible. Right? Interconversion of Fisher. So, yes, Shrey, please tell.
Ma'am, can you please show the first slide on Fisher conjunction?
Okay. First slide, Shrey, hold it. Which one? This one?
Yes, ma'am.
Do you want me
Next
to?
one, next one, next one.
Next one is this one.
Yes, ma'am.
You want to write? Do you want me to hold?
No, just take a screenshot. One second.
Okay.
Thank you, ma'am.
Okay. So we were, I think, here. So I was telling exchange of 2 groups on the chiral carbon. 2 groups could be horizontal to horizontal exchange, horizontal, vertical, vertical, any possible exchange, because whatever you are assuming to be horizontal, vertical is of no importance in 3 dimensions. They are all equidistant. Okay, so if 2 groups are exchanged, then whatever the new arrangement you will get is of enantiomer. That is the mirror image. Rotating the Fisher in the plane of paper by 90 degree, you can never bring it out of the plane of paper. Okay, because whatever horizontal, vertical conventions then will be disturbed. So you cannot flip from paper, but in the plane of paper, like a what should I say, chakra, you can move, spin in the plane of paper. If you rotate by 90 degree or 270, you will again have a mirror image representation. And this we can prove by RS. Just wait. Right? So RS is a very important configuration. First, you have to visualize the tetrahedron such that, or rather, first you have to give CIP priority to the 4 groups attached to the chiral carbon. Visualize such that the lowest is directed exactly 180 degree opposite to you. And for the rest 3, in the decreasing order of CIP priority, draw the arrow. If the arrow goes clockwise, it is right-handed rectus. If it goes anti-clockwise, it is sinister S. Okay. If the arrow goes clockwise, then name it as R isomer. If the arrow goes anti-clockwise, then name it as S isomer. Absolutely clear? Now this is the perfect method. See, for this, even if you see the lowest priority, A, B, C, D, D is the lowest priority. So what you do, you put it on dash. You visualize such that it goes on dash. That is one choice. Or you simply exchange. D and C, I have done exchange. Now I have done one exchange, odd number exchange it is. And then I will do a 2-dimensional arrow for the rest 3 groups. I'm getting R answer. But this was after one exchange. So I will report original structure as S isomer. Is that absolutely clear? If the lowest priority group is not on dash, then bring it to dash by one exchange. Okay. And then draw the arrow. reverse your answer as a final answer. If you are getting an arrow clockwise, you report anti-clockwise. That is the shorthand for wedge dash. Shorthand for Fisher. Please take screenshot of this. It is very, very simple. If the lowest priority group is on vertical line, whether upside, downside, any side, okay, and then draw, just ignore it. This lowest H, ignore it. Give the two-dimensional arrow in the CIP priority for the rest three groups. So bromine to ethyl to methyl. I am going, so I am getting anti-clockwise. So this is S isomer. Is that clear? On if in the Fisher the lowest priority group is on vertical line, then we simply ignore it, draw the arrow for the rest three in decreasing order of CIP, get an answer. Whatever the answer, that is your final answer. But if the lowest priority group is on horizontal line, okay, then again you do the same thing. Let it be there. You draw the decreasing order of CIP for the rest three groups. You get an answer clockwise, report opposite. So if the lowest priority is on vertical, two-dimensional arrow is your final answer. If the lowest priority is on horizontal, then the opposite of two-dimensional is your answer. Absolutely okay. For wedge dash, as I said, if the lowest priority group is on dash, then the two-dimensional arrow for the rest three is the actual answer. If it is not on dash, then bring it on dash. Okay, see methyl and H, I interchanged with the blue pen. I just wrote in a bracket that I have an interchange in my brain. Now bromine to ethyl to methyl arrow is going clockwise, but I have to report opposite because this is after one exchange opposite. So my answer is S. Is that absolutely clear? Right? If a molecule is R isomer, then its mirror image will always be S isomer, provided it has only one chiral center. R and S pair will have equal magnitude of optical rotation, but in opposite direction. The isomer which will rotate PPL in clockwise will be called dextrorotatory, represented by plus or D, and the one which will rotate PPL in anti-clockwise will be called levorotatory and will be represented by minus or L. And there is nothing like R has to be dextro or R has to be levo. It is simply 50-50 probability. R can be dextro, R can be levo. S can be dextro, S can be levo. Is that absolutely okay? In case of one chiral carbon molecule, R and S will be non-superimposable mirror images of each other. Such optical isomers which are non-superimposable mirror images of each other are called enantiomer. In an enantiomeric pair, one is dextro, rotatory by X, then the other will be levo by X degree. Enantiomers have identical physical and chemical properties except for their behavior towards plain polarized light. Okay. Now let us do RS for this molecule. First, you assign IUPAC numbering: CHO, carbon, carbon, C. So 1, 2, 3, 4. Center number 2. Lowest priority is hydrogen is on dash. Highest priority oxygen. Then it will be CHO. Then it will be this big thing, carbon number 3rd. So I'll rotate OH, CHO, big thing. So it is going anti-clockwise. But H is on horizontal. So you will report answer as R. So 2 is R. 3. Same process you repeat, OH, because H is again on horizontal. So we have to reverse the answer what we will get. OH, then this carbon number 2, then CH3. So it is rotating R. So we'll report answer as S. So we'll write 2R3S in bracket in the IUPAC name. Right? Like 2, 3 dihydroxybutanol it is. So in bracket we'll write 2R3S, 2, 3 dihydroxybutanol, like that. See, if OH and H I just interchange, the R configuration will become S. Similarly here, S will become R. So if you see, this is exactly mirror image. So when I'm taking a mirror image of a molecule having more than one chiral center, then each center should be reversing its configuration. R is becoming S, S is becoming R. Absolutely okay. Till here, no problem. How to assign RS? Okay. Interconversion of Newman to Fisher and Fisher to Newman. Yes, theory I'll give you. Theory I'm giving. So first step, whatever Newman you are given, okay, rotate it to have a eclipsed arrangement. Rotate to have an eclipsed arrangement. So this is what you can have. You can have eclipsed arrangement. Bromine. So I rotated H, all 3H, hai. So I rotated H, 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 like this. Now, once you draw this, you have to imagine, right? What you have to imagine as it is a two chiral center molecule. Let me draw and then I'll tell you. Let me make the model. Okay, so let me restart. So I was discussing that how you will visualize this, right? Interconversion from Fisher to from Newman to Fisher. So I was saying that you have to visualize. I hope this is clearly visible to you. On a black background, I guess it will be clear. So you will visualize it such that it is in an eclipsed arrangement first. Okay. Then see any two bonds like this is forming one V. One V this side, one V this side, one V here downside like this. Right? You have these three V's. Now you have to visualize such that any V does not mean that should be orange on orange, green on green. Anything you do doesn't matter. Any eclipse arrangement you take. The only thing you have to maintain is you bring it on table as if it is on only one bond settled on table and the other V is upside. Okay. So you can imagine as a cartoon character also or whatever you want, and then you just have to do press it on the paper. Okay, press it on the paper. For example, if for you I'm talking, left right for us will be interchanged. Okay, so due to camera interchange, so like this. So you just press it against the board now, right? So how you will draw? Now let me share the screen. Shared. So what I was telling, so once you have this imagination, so you will just write, see here I'm writing carbon up one, carbon down one. Okay, we'll convert, remove this carbon and extend the lines later. So upside is white, orange, right? Orange. So you are just pressing. So for you, your right side should be orange, green, white, and green. Right? Like that, you will simply imagine. Then you just remove the carbons, you extend the lines. This is what your Fisher is. W, O, green, O, green, W. This is your Fisher. Now, the point is what happens that when this is in a form of model, it is easy to imagine and understand. But what if it is not in the form of model? It is there in our exams. How will we do there? Okay. So for there, you can imagine simply you bring it to a way like this upward direction is there. Now here again, you have to finalize which one you are taking as a up carbon. If I am taking this as upper one, and this one as a lower one, then I have to be very clear about first this, because without this, you may end up with wrong positioning of left and right. Okay. I hope you are getting what I want to say, that you have to clearly define which you are taking as upper one and which you are taking as lower one. And then once you decide the back carbon if is upper, then uske liye bottom is H. So you put H. Ethyl, ethyl, because you are pressing it just on a plane of paper, right? Back carbon, hydrogen and hydrogen. Front carbon, bromine and deuterium. So bromine and deuterium. Right, left, you just put. After this, you can simply check the RS if you want to confirm. That is the easiest way to have the idea whether you have done it right or wrong. Okay. Interconversion, again for sawhorse to Fisher or Fisher to sawhorse, you have to maintain that they are in eclipsed conformation always. If you want to make a Fisher, bring them to eclipse, then only you draw. If you want to go from Fisher to Sawhorse or Newman, bring them to eclipse and then you proceed. That is a rule. That is a compulsorily involved step. Okay. Now let us revise few definitions. So first, chiral center. We have done it yesterday. All groups on an sp3 atom, which is tetrahedral. sp3, here I am talking of tetrahedral atom, should be different. Right? Nitrogen with lone pair should not have flipping, then only it will be considered as chiral center. Otherwise, it will not be considered as chiral center. Okay? Chiral carbon. sp3 carbon with all four groups different. Then it is called chiral carbon. So you have to check the question whether they are asking chiral center or chiral carbon. Okay. Then comes the stereo center. We discussed yesterday. It could be chiral center, it could be geometrical center, any such center at which if two groups are exchanged and you get a new stereoisomer, then it is called stereo center. Okay. Is that clear? Stereogenic unit, site or group of atoms which generate stereoisomerisms are called stereogenic unit. Okay. Then comes the prochiral center. sp2 bhi ho sakta hai, sp3 bhi. Such center which is achiral now due to two groups are same on sp3 carbon or due to planarity and can become chiral by either exchanging one atom or group from identical groups with something different. For example, if we do monohalogenation of this molecule, then I have two prochiral centers. See, if I introduce bromine here, this center becomes chiral. Or if I would have introduced here, this could have been chiral. So I have two prochiral center. In case of sp2 carbons, by addition reaction, if it can be converted to chiral center. See, this is sp2. When I put Cn minus, this becomes sp3. So this was sp2 and can be now converted to sp3 chiral center. So it is called prochiral center. Definition clear? If there is anything that comes and you want to write, then you have to tell me that please stop. We want to write. Okay. I understand those who are attending individual by their individual gadgets, they can take screenshots, but I'm talking about the entire class. Okay. So if any place you want me to stop, you just unmute or you drop a message. As today you have joined by 2Gadget, you can tell me that hold on for this slide. We need to make a note. Agreed? Okay. So prochiral, I have just discussed. It could be sp2 or it could be sp3. Now coming to enantiomer. Non-superimposable mirror images of each other are called enantiomers. Okay. Enantiomers have identical chemical and physical properties. Okay. In a pair, one is R and the other is S for one chiral center, you can say. In a pair, if one is dextro, then the other has compulsorily to be levo. This fourth point is valid for even if it has more than one chiral center. Racemic mixture, Equimolar mixture of two enantiomer is called racemic mixture. It is optically inactive due to external compensation. Like, what do I mean by external compensation? Light passes from one molecule and gets deviated. When it moves out from this one molecule, it is deviated. Then there is some another molecule on its way which brings it back, and may overall effect becomes undeviated. So with respect to molecule, the compensation of the effect on ppl is done by another molecule. So it is called external compensation. Okay. If we would have talked of mesomer in the next lecture, next slide, then it is internal compensation. Let us move to next. Yeah, here. So if we go to mesomers, molecule with two or more chiral atoms, but is still behaving as optically inactive due to presence of POS or COS, then they are called mesomers. So it has more than one molecule. Now there is a difference that in racemic mixture, one molecule entire was having effect on ppl and its effect was nullified by another molecule. Whereas in mesomer, that effect is nullified within a molecule. Like one set of atoms in a molecule is generating, say, some sort of rotation, and internally the other set of atoms within the same molecule is bringing the effect back to zero. Okay, so mesomers are optically inactive due to internal compensation. Is that absolutely clear? Is due to internal compensation. Absolutely clear? ठीक. So tartaric acid in 1847, Pasteur separated these enantiomeric pair and mesomer. He found that these two are having different crystalline structures, and thus they were found to have two different arrangements. And at that time, 1847, when there was not even proper microscope, so he separated electronic microscope. Simple was there. So he separated the tartaric acid two crystals. One is the mesomer, other is the active pair, enantiomeric pair, with the help of forceps. Mesomer mirror image is superimposable on it because there is a plane of symmetry. So it will have a superimposable mirror image. Absolutely clear, right? So I would like to ask that for a molecule to have mesomer, it should have even number of chiral centers compulsorily. Answer you have to give as yes or no. Okay, so please give me your answer. I'll ask. So for a molecule to be mesomer, it should have even number of chiral center, odd number of chiral center, what type of chiral center, what count of chiral center is suitable for it. Oh, today I don't see Girish in the class. If Girish is in the combined class, you can have a thumbs up from there. No, he's not there also. So he is missing the class today. Okay. So, yes. Tell what should be the answer for that mesomer question I just asked. Yes. Who is answering? From the class, please unmute anyone and tell whether for a molecule to be mesomer, it should have odd number of carbons or even number of chiral carbons.
Even.
Okay. So from there I got answer even. Okay. Rohit, what is your opinion?
Even.
Okay. Rohit is saying even. Last, let us stop for Shrey. Shrey, what is your answer?
Even.
Even. So all of you are of the opinion that for a molecule to be capable of mesomer, it should have even number of chiral center. So let me change. It can have odd number of chiral centers.
Can be both.
Yes, can be. Both is the correct answer. Okay, it can have odd number of chiral centers also. What do you all say? It is not always possible, it is not always compulsory that it should have even only. Now for odd, I am moving ahead in the slide so that I can see this one. Can you all see that this, if a plane is passed through this C number chiral center or 3 number chiral center, it will act as a plane of symmetry and this molecule will then be a mesomer. So it could be any, whatever is available, that could be used. Is that okay for all of you? Okay, okay. So please, I hope you might have written in your notes now that for a molecule to be mesomer, it could have even or odd number of chiral centers. Both possibility is okay. Okay. Moving further. So I was telling you about this pasture in 1847. Now see the Van 't Hoff. Van 't Hoff was like, okay, the structures were different, that idea was there, and Van 't Hoff started working in that direction. He was doing something. He was the first one who had that at a very early age. See, 1852, he was born. In 1874, so he was just 22 years old when he suggested that there is something called chirality. Okay, so he was working under senior lecturers and he found that if a molecule is like this, okay, having 4 groups different, then there is something like this, 4 groups different, right? So then he said that I am having a structure which appears to be same as the first structure, but there is something different which I cannot explain. Let me draw the structure. Give me 1 second only. Okay. Go back. Now see what he was trying to prove. Can you see these 2 structures, or let me put the camera a little more down so I can show you. Is it? Yes, now you can see, right? So see these 2 structures, right? So he was saying, okay, if there is this structure, 4 groups different, and if I bring you this structure, 4 group different, if I say, so if you are not having both placed together, you will say, what is the difference? 4 groups different, same thing, orange, purple, green, white, what is the difference? So Van 't Hoff was the first person who told that they are different. How and why? He said, I don't know much, but they are different. Okay. See, if you have a mirror here, it is a mirror image relationship in there. And if I try to superimpose, okay, and when I say superimpose, it does not mean exactly have to do like this. You can do whatever rotation, whatever flip flop thing you want, but it will always remain non superimposable. Okay, whatever you do, if I do this, then the green and red is disturbed. If I want to place, okay, green and red should go hand in hand, then the white and purple are disturbed, right? And that simple thing that you have a mirror image of these hands, so they are superimposable. Whenever we have a picture, we have this fish like thing that, okay, no, they are non superimposable. Does not mean that if you go by this method and now they are superimposable. This is not superimposability. Superimposability means it should be nails on nails, skin on skin, palm on palm, exact. That is what you will call as superimposability. So this is non-superimposable and this is superimposable is a misinterpretation. Absolutely clear. When you have a superimposition, you should have exact. Like, for example, if I have a mirror over here and you take an image and I walk on the image, then it is perfectly superimposable. So, superimposability was first of all suggested by Van 't Hoff. And at that, now I have to stop the camera, let it be. So, coming back to where we were. So, the first initial person who was telling this at a very early age was Van 't Hoff. And Van 't Hoff was criticized badly by the senior chemist. Kolbe's was a big name, Kolbe's electrolysis, Kolbe's reactions. So he criticized Van 't Hoff, and there was an entire group of senior scientists. But he stuck to his thought. And in 1901, he was the first person to win the Nobel Prize in chemistry. Okay. And 1902, the second was Fisher. So initial two Nobel were for chirality, for optical isomerism. Mesomer can have odd or even number of chiral centers. Let's come to what is called diastereomers. Now, what is diastereomers? So such stereoisomers which are not the mirror images of each other. Okay, they could be geometrical isomer, they could be optical isomer. They are called diastereomers. The only condition we want is they are not mirror images of each other. They have to be stereoisomer. Like I cannot put any random two molecules which are not mirror images and thus they are diastereomers. They should be the one which are non-superimposable, which are not even mirror image of each other but are somehow stereoisomers. Then only they can be in the pair, as a pair declared as diastereomers. Right? A mesomer is diastereomeric to anyone from an enantiomeric pair. Both GI or OI diastereomers will always have different physical and, of course, chemical, so we have already talked, physical properties. Okay. For example, again, take a screenshot of this tartric acid thing. I don't want you to learn, just have a general idea. See, plus tartric acid minus tartric acid. So they are enantiomeric pair. So same melting point we have got. Mesotartric acid has 146, 148 degree. Specific rotation plus 12 minus 12, 0. Density 1.7598 for the enantiomeric pair, 1.66 for the meso. Solubility, if we talk in water, then enantiomer has 139 grams per cc, whereas mesomer has 125 grams per cc in water. Clear? Now, which of the following compounds could have mesomer? I think it's a very usual and a common question. Do it. 1, 2, 3, 4. Which one of these will have mesomer?
Excuse me, ma'am.
Yes, bolo beta.
Ma'am, any reason for such a decrease, ma'am, in properties when it comes to meso?
No, no, no. No, we don't have as such any reason.
Purely experimental.
Yeah.
Okay, ma'am.
So which of the following compounds can have mesomer? What should be your answer out of 1, 2, 3, 4? No one?
1, 3, and 4.
3 and 4. Oh,
Just 1 and 3.
Okay.
1 and 3
4 is not
right.
optically active.
1,6-hexane diol is not even optically active. So first thing you should have a chiral carbon and then you should have a plane of symmetry. Right? Then only you can call it, okay, these are mesomers. Otherwise, it is not mesomer. Is that okay? Moving further. Oh, pseudochiral is a heavy topic. I don't want to do it in end of the class in hurry. Let me see what I have more. Okay, epimers I can do. So they are the diastereomers which are optical diastereomers, not geometrical. Such diastereomeric pairs which have identical configuration at all the chiral centers except any one, and that one is not fixed that it has to be carbon number 1 or 2 or 3 or 4. Any one is having a difference. Rest all are exact copy paste. Then they are called epimers. For example, if you see in this, I have 2R, 3S, 4R, 5R. Okay, 2R, 3S, 4R, 5R. D-glucose. Then I took this one. In this, I have 2R, 3R, 4R, 5R. So 1 and 2, I think this is D-mannose, right? So here you see the only point of difference is this second one. Rest, they are copy paste, 1 and 2. So 1 and 2 are epimers, and you have to mention at which carbon it is epimeric to. Okay, so I wrote here 1 and 2 are epimer at C3. 1, 2, 3. Right? If I similarly talk of third one, so 2R, 3S, 2R, 3S, 4R, 5R. Okay, 5R, 5S. So 1 and 3 are epimeric at C5 carbon. So C5 epimers. 2 and 3 are not epimers because they have 2 point of differences. Am I right? 2 and 3, they have difference at C3 also, and they have difference at C5 also. So they will be simply called diastereomers, not epimers. So for epimers, any 1 point of difference. For anomers, it is a particular carbohydrate chemistry you might have seen. Epimers are only when the carbon which is chiral in cyclic form and achiral in open chain, then only it is having epimer. Alpha D-glucose, beta D-glucose, for those we use the word epimers. Okay, for there we'll use the word epimer. All diastereomers are epimers. That statement is false, but all epimers are diastereomers. That statement is true. All anomers are epimers. True, but all epimers or anomers will be false statement. Is that absolutely okay, Anna? And from resolution, I'll carry forward from tomorrow because these 2 points, pseudochiral, resolution, I have to be a little detailed. So anyone, if has any problem, please ask. Anyone? If nothing, we'll continue from tomorrow here. Both the topics need slightly more time. No one? Okay, then you can continue with your next class.